So here we have some kind of tooling, composite tool, trim tool, whatever it may be. And let's focus on it. We want to slice this part at an angle. If we sliced it the classic horizontal way that we've just done, we'd need loads of infill, loads of skin in order to print this top surface, and it would be a hideous mess. But in large format printing, slicing at an angle, so rather than your planes being this direction, if they're at 45 degrees, this top surface here is actually a 45-degree angle rather than a complete 90-degree shear. And that is an achievable overhang. So all we do for that is we pick our angular slicing mode, and then we define around which plane. So we have our X, Y, Z over here. So we're defining, in this case, 45 degrees around Y. But we can also use things like reference planes, or even have an inbuilt algorithm to determine what is the optimal slicing plane automatically. And all the other settings are the same. So we've got layers, walls, infill, skin, etc.
Yeah, the best plane is very handy. For me as a designer, sometimes I want to make gymnastics around that, especially when it's a design. But it's great to have all options.
Exactly. So now you can see here that we are at a 45-degree angle. We also have our tool rotations view, and these will show your X, Y, Z TCP. So here we have our X, Y, and then Z goes into the nozzle, and that'll be blue. And we can see here, if I just filter out single layer so it's easier to see, that on every point we have our X, Y, Z TCP, and it's automatically angled it to 45 degrees. So while we have the ability to manually change our tool rotations, for all our slicing modes, it is done automatically based off the information provided. That saves a lot of time. Because this part might be some kind of composite tool, I might want to reposition where my seams are. I may not want them up on this corner here. So we can, say, use different seam settings to reposition them. In this case, I've actually used a combination of operators in the software to extract a polyline that is the same length as the part. So see here, it's the nice exact length that I need it. And then I'm going to move it to this edge here. And then the seams operator, I can use a reference polyline. And this could be a 3D polyline. It can be created in CAD and imported into the software. And that means we can place our guides exactly how we want them across the entire shape of the part. And I've also turned on zipper mode. So while the seams are going to be created along this wall, they're going to be spaced plus or minus 10 millimeters either side. So let's take a look at the results. So you can see we've now got it along this edge, and we can see that the seams are also zippering. So while they're along the same general guide, they're not stacked directly on top of each other. So that can help improve quality.
Yeah.
In the software, we have lots of ability to filter, and that's important because you want to provide, different fixes, optimizations, and improvements, but you want them targeted. So here I'm filtering out our walls. So I'm getting rid of the infill because I don't need to optimize the infill in this scenario. I'm just looking at my two kinds of walls. And then I'm using our optimize operator. So this is a very powerful operator. We can optimize for a number of different things. So we can analyze the curvature, sharp corners of the polylines. We can compare the thickness of the polylines to the CAD file. And we can also look at overhang, or we call it cantilever, because the founders come from a nice architectural background. So that's why they call it cantilever, but it's overhang. And we can, with some parameters, analyze around that data. We can set limits to what we're looking at as well. And based on the analysis, change some feature of the polylines. So here I'm looking at thickness, but we can also say apply a speed multiplier or change our layer heights even. And we can multiply or give it a specific value. So here I'm looking at the corners, and I'm going to reduce our extrusion at the maximum curvature. And the reason I'm doing that is because a lot of the time in large format printing, you have natural accelerations, decelerations of the robot or the gantry. So as you approach sharp corners, your robot is going to be cruising at a normal speed, and then it'll slow down, and then it will come back out. And your RPM will be of your extruder will be at a consistent rate, assuming that it's at a steady speed. And that often means you're over extruding at the corners. This is seen a lot of the time. So what we're doing here is we're actually reducing or applying like a difference in extrusion rates in the corners so that it will even out and give you the exact extrusion that you need. So we can see from the analysis, it's highlighted where all of our corners and turns and curves are. And it will apply this multiplier to the thickness of the polylines. So I can actually go to a thickness view, and we slice the part with a 10 mil wall thickness. So most of the parts are 10 mil, and you can see we have 7.5, so it's been multiplied at these right angle corners here. I could even turn on the split bead view, and there will be a difference as well. In the real world, the intention is that it all evens out. But
and the pipe is also reflecting the actual thickness, right?
Yeah, exactly. Another quick optimization I'm going to do is combine our walls together. So by default, we have two walls here, and they will be two discrete extrusions. So let's do the outer wall, stop extrusion, move, start extrusion, do the inner wall, and repeat with the infill as well. But it would be neater, quicker, if we didn't stop and start our extrusion in between those points. So what we can do is we can use our make continuous operator. So now you see that our inner walls have gone, but that's because they've actually combined with our outer walls. And now at the location of the seams, we have our walls combined, and the zipper remains. So they've combined together nicely. And we can combine that back with our infill that we filtered out earlier, sort it by layer to make sure it's all printing in the correct order. And then we can feed it into our toolpath operator to print the part. So we can show you how the angle of the tool is all done automatically. So we didn't have to do a thing here. But we'll look at the thermal simulation.
It is important to note here that definitely there are many actions to be done, but at the same time, this is needed after some years of experience making parts. You need to have that kind of flexibility. But for us as well as software developers, we've seen that before we come into full automation, we need to nail every detail. And that's the next step and the next stage of Aibuild, combining these operations to get into full automation. But first, we need to get the basics, get parts out as quickly as possible for our customers, and have the whole gamma of possibilities here for successful prints, but also safeguard us for the investment we put for a future that is fully autonomous.
Exactly. And I suppose it's worth saying that there's a few steps here, but this whole thing probably takes around 10 minutes to put together. And on top of that, because this is all parametric, if I wanted to change some settings of my slice, I don't have to delete all this work up here. I can make a change, say to my wall thickness or number of walls or my infill density, whatever you need to do. And anything connected to that will recalculate as well. So I don't have to delete Control-Z and go back. I can keep making iterative tweaks and see the end result within a matter of seconds.
And then, of course, that's your intellectual property. Ultimately, what I say to many people, this is your engineering workflow, and we provide a platform for other people to develop their own unique slicer. So every time can be very unique to what they built, which is very powerful.
And on that kind of idea of individual slicer, the parametric aspect or nature of the software, I could even change the CAD file at the very beginning. And that connected to everything else will recalculate as well. So maybe for your process, your technology, this workflow here is the perfect workflow for printing composite tools at a 45-degree angle. And you need to do 100 of these a year. You don't need to recreate this workflow 100 times.
Yeah.
You can just reload the file and it will recalculate and do the whole thing again. Maybe you need to reposition it or move that polyline guide, but that's literally it. You can do that super easy. So it is quicker, incredibly flexible, and powerful. Just to finish this one off, we have our thermal simulation. And because it's at an angle, our start and end layers are much smaller because we're starting and ending at the corners in this kind of boxy geometry. So even though we have a perfect speed for the bulk of our part, it's too fast for the ends. So if we want to automate this, we can do. In the toolpath operator and the movement speeds, we can turn on layer time management. And here we have a few automated features to use. The quickest one is this first one here, where we can adapt the speed based on given layer times. And that's what we've done in this example. So for this material, we're provided a minimum and maximum layer time, and the operator will adjust the speed for each individual layer in order to hit this layer time. So that means you're managing your thermal buildup, you're not going too slow and you're not going too quick. Other ways of doing it, the second one, we can provide a minimum and maximum speed, and then it will adjust the speed to thermally optimize it if it's within the window. And then, of course, for metals mainly, we can simply add a pause between layers for a minimum layer time. Not great for polymers. Your material might burn in the extruder, but it's there anyway. And we can see from the second thermal simulation that we have much more green, which is exactly what we want. A couple small outliers, but far better. And that's all related to the material that you pick. It will have material properties associated to it, thermal properties, layer time options, things like that.